Hi, hello everybody. Good morning, good afternoon, wherever you are located in the world. A very warm welcome from Siemens to our control panel webinar series. Today's topic, how a short circuit calculation influences your design. My name is Jorge Olarte. I am a business developer and technical consultant in Germany. I've been working for Siemens for more than 13 years now, and I've held different positions as product management, application consultant, and business development. I've also been working as a business unit responsible in Siemens Colombia, South America. It's an honor to be your speaker today. Please, if you have any questions as we go along, you can contact my colleagues via chat at any point. They will answer as soon as possible. Don't worry if they do not respond immediately. All questions will be dealt with. I will also like to invite you to join our LinkedIn community for industrial control panels. First of all, a little overview of the tool that we use for this webinar On24. I hope that you have opened the application in Google Chrome to provide you the best quality regarding audio and graphics. If not, I would like you kindly to close the application and sign in again in Google Chrome. The overview actually of the interface you're looking at. On the left hand side, you will find a Q&A window. This is for questions and answers. You may submit any questions you might have during the webinar to address them directly to us. We will try to provide you a clear and fast answer. And if there is not enough time, we will follow up with you after the webinar. In the lower area of the user interface, you will find some colored icons. The yellow icon is like the help button for the On24 tool. Please remember that everything that we show today is based in the interpretation of Siemens. The application of the standards directives is based in this. We assume no liability for the correctness or completeness of their applications. You are responsible to check whether the application complies and for the safe and proper installation. Well, the agenda for today will have a small introduction just to get the basic of the knowledge for all of us aligned. We'll talk about the protection equipment, especially for short circuit, of course, a little bit about short circuit capacity, and we will also talk about selectivity versus backup protection and how actually the short circuit calculation influences in all of this. And we will do an example in our CMATI design tool about to talk about the short circuit and how it actually influences your design. Well, in every electrical installation, we have some possible faults, and these are actually based in overload. Some of them come by overcurrent or over temperature. And when they come from overcurrent, we will have to look into overload currents and short circuit currents. This is why actually the short circuit consideration is so important for this. When you select actually the possible short circuit protection equipment, you'll have to take into account the rated current, the short circuit breaking capacity, one of the topics that we're going to discuss, and also the time how actually this happens. The issue that any device that has a capacity to carry current flow is actually being manufactured to a certain rated current. When we work at this rated current, of course, the flow of current generates heat, but this heat is easily dissipated through the outside of the device. But actually, when we work to a higher current or above this rated current, it creates more heat. Now, the device cannot dissipate as easily the heat to the outside, meaning the temperature inside of it actually rises. And when we do not process these overload currents, well, we will have the issue of the short circuit currents. When we come and talk about the timing of the protections, actually we will see some curves in the overload range and these type of curves in the short circuit range. Actually, what does this mean? These are some tripping curves. As you can see, the overload range actually comes above the seconds range, meaning that actually the overload protection allows the load to go above the rated current for a determined period in seconds. Now, with the short circuit range, you see that we're talking about almost something instantaneous. As soon as the short circuit current fault occurs, the device that is protecting this fault opens in milliseconds, almost an instantaneous tripping. Also, in this graph, you can see that basically the short circuit current starts at 12 times the rated current. But actually, you can move along depending the type of breaker or protection device that you have. It can be higher or lower than this. We will get into this, of course, in our presentation. In the market, you're also able to find not only thermomagnetic devices like the one that you have just seen, but also only magnetic, meaning that only the short circuit protection is made. There's nothing in the overload side. Why is this so important? Because actually when we talk about the protection devices and we divide up our electrical circuit into in-feed and load feeders, it will make much more easier also the selection of the devices. In the in-feed, we will need products or devices that actually allow us to have a short circuit protection of the control panel, an overload protection of the cables inside of the panel, and the main switch for safe isolation of the system. Basically, we'll focus here at the first step in our presentation. Actually, the IEC 6204 electrical safety of machinery allows us to have a disconnecting device that is actually under 6947-3 or 6947-2. This is basically fused designs or fuseless design as circuit breakers. Difference, of course, between them is based upon, depending on the market, in prices, as availability or demand also occurs, but also because as soon as a short circuit fault appears, in the fuse design, fuses have to be replaced. Whereas in the fuseless design, you just need to reactivate the circuit breaker. There are actually two types of circuit breakers, and they are different depending on the behavior of the short circuit protection. When we have ACBs, or air circuit breakers, we call them a zero current interrupted. As you can see in the slide, the time of cutting is actually 10 milliseconds when we talk about 50 hertz, meaning the complete area below this curve is the energy that is transmitted from the incoming of the air circuit breaker to the outcoming of the air circuit breaker. When we talk about MCCBs or multi-case circuit breakers, we call that they are actually short circuit current limiting devices. This means actually that they can open and activate or trip in a much faster way. We talk about only 4 milliseconds, as this is shown in the slide. Meaning, as you can see, that only this part of energy is the one that is transmitted from the incoming of the device to the outgoing of the device. Meaning the installation below this MCCB will have smaller short circuit faults when compared to the incoming of the circuit breaker. Let's have an example of this. Imagine actually that we have a 37 kilo amp short circuit here at this point, just below Q1, affecting the whole bar that connects Q2 and Q3 as separate circuits. But actually in the branch of Q2 and below this one, we can actually see that the whole short circuit current is transmitted below this breaker. But actually in Q3, in the branch of Q3, 25 kiloamps only go below the breaker, meaning actually that Q2 it's a non-current limiting device and Q3 is actually a current limiting device. Now, let's focus a little bit more in the load feeders. For the load feeders, actually, we will need a short circuit protection of the load feeder, overload protection of the cables and the loads, and isolation or disconnection of the individual load feeders instead of the complete installation. Yeah, when this happens, we can actually have two possible installations or designs: fused installations or fuseless design. Different between of them, as you can see, one again is based in fuses, and the other one is based in MSPs as motor starter protector in Siemens Sirius 3RV or Centron 3VA. Also, depending, you may have soft starter or frequency converters instead of the contactor. Here, of course, it will depend whether or not you need the availability of these products after the short circuit. Then the fuses are most often used. What happens with the short circuit capacity and actually what does this mean? In our electrical installation, there are three types of short circuit: the one pole, the two pole, and the three pole short circuit. As a rule, the one pole short circuit generates the lowest short circuit current, and it's the one that you need to protect in a really fast way. Of course, depending on the load, as we will discuss later. The three-pole short circuit current, as a rule, is the highest short circuit current that is generated in your circuit. And this is the one that we need for the short circuit breaking capacity. Product and circuit breakers have often two characteristic things inside of them, the ICU and the ICS. The ICU is actually the ultimate short circuit current breaking capacity, and the ICS is the service short circuit breaking capacity. ICU is actually the current that must be disconnected twice by the circuit breaker without damage. Then the device must be replaced or examined. As whether as the ICS, this current must be disconnected 3 times by the circuit breaker without damage. The circuit breaker must then be capable of carrying the service current. Dimensioning according to ICU is recommended if the risk of a short circuit current is really low, and the ICS dimensioning is recommended if you need a very high plant availability. Let's see an example of how you select your devices for the short circuit breaking capacity. Let's see this example. We need to replace Q1. Q1 must be a breaker that carries 30 amps and must protect 30 kiloamps as the highest short circuit current that you will see in this point. Imagine that in our stock you have 3 different 32 amp breakers. 32 amps as a rated current for these breakers actually works for Q1. The difference relies in the breaking capacity. For A, we have 15 kiloamps of short circuit breaking capacity. For B, we have 37 kiloamps, and for C, we have 50 kiloamps. What do you think will work? I'll let you think for a little bit. Well, we will mark them as work and doesn't work in an easy thing. 15 kiloamp actually doesn't work because this is below the highest short circuit current that I will have in my circuit. Actually, my short circuit breaking capacity must be above the highest short circuit current that I will have in my circuit. If not, this will explode or break. Yeah. Now that we understand this, let's see a little bit commercially what are the main differences of these breakers. Most of you would assume, well, the one in 50 kiloamps is bigger than the one in 37 kiloamps or something else, but actually they can be the same sizes. Actually, in the Siemens portfolio, these are the same sizes. They just use different materials inside of them. The real differences in all the markets already seen is actually the price. Why will you use a 50 kiloamp when you can use a 37 kiloamp for the same solution? This will only make your solution expensive. So this is one of the key things that we need to understand actually, that when we use devices with higher short circuit capacity, they will most often be more expensive and make our design or solution expensive to the customer. Let's talk a little bit about selectivity and backup protection. What does this actually mean and how does this actually also influences my design? Well, if we focus on the left hand side that we see here, let's imagine that we have a short circuit current or fault here. As you can see, Q2 is the breaker or device that should open and protect the circuit affected. But actually, Q1 also trips, meaning that we are not being selective because all of the circuit here in the gray area, it's being affected. So we disconnect everything. When we talk about being selective, now we can focus in the right hand side where this same short circuit appears, but actually only Q2 opens. Q1 remains closed, remains active, letting the current flow to the branch of Q3 and only disconnects one of the branches. This is being selective. Of course, what's the difference? How can we achieve this? Again, we talk about to invest money in different types of circuit breakers or what we call trip units that may help us in this. Now, what is backup protection? Now, once again, if we focus in our diagram that we have here, imagine that we have a short circuit. And actually Q2 opens and actually Q1 also opens, giving and remaining both of them disconnected, meaning we are not being selective when we compare Q1 to Q2. But actually, imagine that the Q2 has actually an ICU of 15 kiloamps, but the highest short circuit current or fault that I can have in this point is actually 30 kiloamps. Why is this possible? Well, because you can see Q1 is also opening. The current limiting upstream device, Q1, must be a current limiting device, supports the downstream protective device, and must disconnect overcurrents that are greater than its own short circuit breaking capacity. This is why you can have Q2 with a short circuit breaking capacity less than its higher short circuit current at this point of connections. What does this mean? Well, if you're not being selective and you actually have backup, you can actually have a lower cost solution because you will use lower short circuit breaking capacity breakers in this. But the design, it's totally okay with the standards. When we talk about starters, we will usually talk about contactors. Contactors usually have a really low short circuit breaking capacity, based in 5 or 10 kiloamps maximum. But what happens is actually contactors don't go by themselves. They will always have something to protect them, either a motor starter protector or a breaker. As you see here, we have type tested combinations in Siemens where we have a direct starter with a motor starter protector plus a contactor, and these have been tested up to 55 kiloamps or 50 kiloamps. Now imagine that we have these load feeders in a control panel like the one that you see here with an infeed of 70 kiloamps, with 5 direct starters of 16 amps that have been tested up to 55 kiloamps, 4 starters of 25 amps that have been tested up to 55 kiloamps, and 1 starter up to 32 amps that has been tested up to 50 kiloamps. This means that all of this control panel will actually go up to 50 kiloamps. The tested combination with the lowest rating will determine the complete rating of the panel. Now that we have checked this and we understand a lot what's the difference between selectivity, backup, short circuit capacity, and what the different type of protection equipment, let's move into our own Simaris design tool. First of all, imagine actually that we're trying to show you how with tools you're able to make an easier engineering design and documentation. Especially in this type, we will talk about short circuit and line dimensioning. Of course, device selection is also tested here. Simaris design actually it's tool where you can dimension electrical networks on the basis of real products for medium and low level. We will focus basically in the low voltage, just to be clear. The dimensioning in this tool is generally accepted by engineering practice. It's based in IEC standards. It calculates short circuit current, the load flow, the voltage drop, and the energy balance, and this is why we're going to use it today. Remember that Simaris Design is a free of charge tool that you can actually download in this link that you see here. It's available in two versions, Standard and Professional, and I myself today will show you the basic license. This basic license can work for everything that you want in a really easy and neat way as I will demonstrate today. The other good thing actually that Simaris Design has is that it will give you complete documentation for your project that you can hand over to your customer. And once again, it's based in the standards. Let's start now with Simaris Design. As soon as Simaris Design opens, it will pop up this window. It's a window where you can start to create your own project, open existing projects, or even tutorials. Let's start with a new project. As soon as I click next, it will ask me for the project name, project description, my name as a planner, and some comments if I would like to. As for now, we'll call it test 1. Then the medium voltage data. Here, the medium voltage data, I often do not change it, especially when working with control panels, because the impact should not be that much. These are the typical values that all usually are used for medium voltage. So here I usually click next. Then for low voltage, of course, I have to check out nominal voltage. For many regions, as you can see here, it's available. 400 as in Europe, 440 or 480 in Americas, and others up to 1000. I will keep it as 400 volts. frequency can also be changed from 50 to 60. And there are some, let's say, critical things that we need to understand and to get to know why they're here. The permissible touch voltage is one of these critical things. This is based in the safety to touch when something might be energized without us wanting to. 6204, the safety standard for electrical machinery equipment, it's based calculations in the skin and health of the user of this. Of course, there are some restricted applications when you might be wet or there might be high humidity. This also takes into account impedances of your body. 90 to 95% of all the applications have been calculated and work with this 50 volts that we have here. But of course, if you need to change it to 25 as a 24 volts DC or 12 volts, we can actually have it. We will leave it as a 50. The standard allows us to do it like this. The other thing that is actually really important is the ambient temperature of the device, meaning the device inside. So this will be inside of the cabinet. Often, fuses go more in the infrastructure market. Well, the fuses are often tested to 45 centigrades. And this is a most critical protective device. These are the fuses. But actually, starters, MSPs, and breakers are often tested up to 60 degrees. So of course, depending on the application and your design, you will place it here. We often leave it as 45 if fuses are going to be used. And as you can see here, as soon as I get out of 45, it tells me that I'm out of the standard 45 because of fuses. And because this is a tool that's mostly used in the infrastructure designs, we leave it like this one. Number of bolts, 3 or 4 if required, so earth fault detection. And then we have also the voltage reference point. According to 6204, the reference point is actually the secondary terminals of the transformer, meaning this is okay and we'll leave it at this. And then the maximum permissible voltage drop in the network, which actually, once again, by our standard 6204, it's maximum 5%. Then maximum and cross section areas of the cables that you will use, and whether or not you would like to have your protective earth and neutral conductors binding or not. Often in infrastructure, you have a TNC network based on a combined network, and in TNS, you will have a separate, meaning you have a protective earth and a neutral conductor separated. So actually, we often do not select this here, especially when we are talking about control panels once again. Then we basically click finish and we are able to start to design our network. Here I will show you some examples of what we have seen and others that we have not talked about. First, let's start with a transformer. Here I will add a transformer, low voltage transformer. As you can see here, I can select the system or the network configuration, either TNC or TNS. I usually keep it as TNC. If I actually do not know this, I'm also able to click here in the info box. And with the info box, I will have the information of what I am looking at. Then I'm easily going to select the type of switching devices and the cables connection that I have here. Basically, let's say that this is 20 meters away, the transformer from our first distribution board. There we go. Then let's start with a distribution board that I will click here. And this distribution board will be basically inside of the panel from it, and I will have here to our control panel, let's say 25 meters. Then inside my control panel, I will have a couple of loads. Let's say that we have here, for example, once again, 50 meters away. Let's try this one. It will be a 7.5 kilowatt motor. I will have 5 of this. As soon as I click next, I will be prompted to selecting the type of starter or dimensioning the type of design that I will use. I will go first for fuseless design as a direct online starter or reversing duty, start delta starter, soft starter that I have here. Yeah. First one, I will leave this one as a direct online starter without overload relay, meaning the protection of the overload will be also in the breaker or MSB that goes here. When I click finish, you can see I'm having the complete dimensioning and I can see my network really good. Here I'm going to add another one. This one will be for now, once again, 25 meters. This will be a higher motor, 15 kilowatt. I will have 7 of this. Once again, direct online starter. There we have it. Now I would like to show you something about the cables. Here inside of the panel, I'm able to show you a little bit of the cables when I double click on the cables, as you can see here, and see the properties of my wires and cables. For example, this one, it's a copper with PVC and with cable design. The installation type is what's really important. Installation type C, once again, as this is a infrastructure, comes as a multi-core cable light plastic threaded on trays. Basically, this doesn't happen inside of our control panel. In our control panel, we usually have type B1 or B2. These are multi-core or light core cables in hollow ceilings or cellular floors. B2, as you can see here, are the same. These are the ones that we use inside of our control panel. So I'll leave it as B1, making this change here. Also making the changes in the other cables so that it actually takes into account also the heating and the type of installation that I will do for the calculation that the tool does. Okay, let me just take a little bit more of notes here. Let's take one that will be a little bit nearer to us. Once again, 15 also. This one will be only one. I direct a start delta starter here. Remember, this is only an example for the basics of our calculation that I will see here. Good. I just moved this so that you can see that, of course, we have unchecked circuits. There are some incoming circuit that's not loaded and something that actually is not being dimensioned already. The first thing that I have to do is actually I click play here. It tells me it's not possible to undo the dimensioning. Of course, I need to first flow this and I need to activate, as you see here, my power supply. So my power supply is a transformer. It's here. It's already been calculating everything. And now you will see that in all of the devices that I have here, I have now some references. Let me just make a small zoom into this one that you're able to see it. And you see it here. For my transformer, it's been then mentioned. For my circuit breaker, now I have a 3VA. This means an MCCB, a molded case circuit breaker. As you remember, this is a current limiting device. Yeah, we will see how it looks. And then I have also other circuit breakers and contactors here in the load side. Okay, this view is actually called the single line diagram with the device parameters. I will click here as you have seen in this icon and I will be able to see the current flow in these ones. But the most important that we want to focus in is in this single line diagram with short circuit load. When I click here, you will see that in my transformer, I will have right below our MCCB 10 kiloamp as a maximum short circuit current and 6 kiloamp or 6.7 kiloamp as a minimum short circuit current. Then I have another MCCB here, and as you can see here, both of the currents have been decreased because of our breaker. As you can see, once again, as you remember, the maximum short circuit current that we see here is the 3-pole short circuit current, short circuit fault, and the minimum is the 1-pole short circuit fault. The most common to happen short circuit is obviously the 1-pole short circuit. Now, if I go into these motors that you see here, and these are also called stationary loads, you will see, for example, that
the minimum short circuit current, that is 376, and this is around, let me just move along this one, 376. It's been disconnected in a really nice way. This is something really important. According to 6204 and 61439 standards, our IEC standards, I can actually disconnect a non-stationary load that has no direct contact with people, with personnel. Actually, I can disconnect up to 5 seconds. Okay, take this into account also for your design. But as you can see, this is doing it by yourself. The other good thing that you can see here in my left hand side is that Simaya design has a target of dimensioning. This is either backup protection or selectivity. And this will also change your design, and this will also make your design either cheaper or expensive depending on your customer and depending on what you need. Basically, if we talk about infrastructure, you will usually go for selectivity methods because you will want to disconnect the branch where the fault has happened. When talking about control panels, it depends because basically when you disconnect a motor into a machine, you often will like to disconnect everything. So here, the selectivity won't be that important. Here, basically, you will go sometimes for a backup protection, making your solution more attractive to your customer. Then again, you will have to commend this to him whether or not he wants his backup or selectivity. So remember, every time with a backup dimensioning, you will have a cost advantage. Now let's make some changes that you see this in real life. I go to my transformer or to my power supply, and the first thing I will do, actually, let's go to the devices. This is a 200 kVA transformer. Let me just double click on it, and let's make it actually a bigger one. Remember that we have almost 10,000 kiloamps as a maximum short circuit current. What happens actually if I increase my power supplies? As you remember, I had 10 kiloamp. Let me just redimension this again. And let's go and take a look at the short circuit view as soon as this is dimensioned. As you can see, all my short circuit current faults have increased only because my transformer has more power than before. Also, all of the data, all of the products now must comply and now must support this type of kiloamp rating, meaning the highest the short circuit current is and the higher the power is, the highest the short circuit breaking capacity of the products will be, whether they are backup or whether they are selectable with selectivity. You will need this. Yeah? Now let's imagine, as you can see here, that now I will need to comply in my control panel with 26.7 kiloamps. What will happen actually if this won't be at 20 meters length, but actually 50 meters length from the transformer? What will happen now? Well, you see this is calculated again, and the short circuit. Now you see this is calculated, and the short circuit currents have also decreased once again, meaning the cables can attenuate the short circuit current rating. Yeah? Especially now, let's see in our control panel, we have actually 20. What happens if this is actually not 20, but 50 meters away? And I recalculate again. As you see, automatically my short circuit current has decreased. Why is this so important? Once again, one of the invitations for the event was, well, your customers always ask you for a control panel that complies with 50 kiloamps. But actually, control panels are not near the transformer. They are downstream all the installation near the machines. 50 kiloamps is usually used by EPCs and designer as the whole installation needs. But actually, when you go and you consult and you ask some questions to your customer about the distances and about where the control panel will be installed, then you'll be able actually to crack out a lot of information and even tell him that he doesn't need a 50 kiloamp control panel, that he needs a 25 kiloamp or a 17 kiloamp. This will reduce his costs, your cost, and you will do a better design for what actually it's needed. Now let's go for the motors. Remember that the motors I had 50 meters, and then this cable is actually a cross-section phase conductor of 4. What happens if I actually have a higher cross-section area? See here that I have 10, that I have here 1000 amp as a maximum ampere rating, as a maximum short circuit current. What happens now? Now it's even higher. Why? Because I'm making my cable bigger, and when I have a bigger cable, the power can transmit more easier from one side to another, meaning the short circuit energy can flow in a much easier way in a bigger cable than in a smaller cable. You see? So here, the attenuation, I cannot see it actually, I'm amplifying the short circuit fault. Now, what happens once again if I bring it to 4 as it was, and again, I put it even a bigger cable. Remember it was 50 at the start and I had 1000? Look, now when I have 100 meters, I actually have only 500 amps as the maximum short circuit current. Why is this locked here? Because I've made some changes for the starting of the dimensioning. Also interesting thing here, as you remember we discussed about the type tested combinations. Here, all the solution that's in my design gives you in the starters are type tested combinations. If I double click on it, you will see that it tells you you cannot change any one of the products because this is a type tested combinations. Under IEC standard, you cannot change, for example, the contactor after installation. If you do this for a different type of contactor or one that is not tested with this MSP in this case, you cannot confirm that this will actually go up to 150 kiloamps like we do in our type tested combinations. It has to be the same reference of contactor. This also has to be placed in the documentation, and once again, it's a way that you can argue with your customers in how the design for him it's better, of course, when using typeset combinations from Siemens. Now that we come here, I'd like to show you something about the graphs and the selectivity graphs that I see here. Let me just be here and let me just stand in the one in the middle. This breaker that you see here is this breaker right here with this envelope that you can see. Yeah, this one, black one, is the envelope of the downstream devices, and the red one is the envelope of the upstream devices. Well, as you can see, we're being completely selective in a really nice way. Even though we're looking for a backup protection, as you see here, we're being also completely selective. And this is because of the high power that we have placed in our transformer. If I change it again, as you remember, we were working with 2 point, with, let's say 100, or let's say that it dimensions this automatically. I can click once again that it dimensions everything. I get some data out of it, and then if I come again to a protection device that I wanted, you will see that now, since this one is not so big, I'm becoming a backup protection, but I am not being selectable here because it is almost the same and the same graphs. You see, it's almost the same. So actually, here I do not know which breaker will trip, either in overload or in short circuit current. Just take this into account. Now, as a project output, I'm able to have project documentation, device device settings, but also the short circuit currents, the selectivity and curves documentation, and this network diagram as a PDF. It's also possible. When I click here, Start Output, all the documents will be placed. When I click Start Output, All documents will be placed, all warnings of course will be shown. Remember, this is just an example to show you actually how we can work with our customers together to find a better solution for them with the use of tools. We can have a much effective solution and efficient solution for what your customer needs. I would like to show you the project output documentation when we have the names of everything, the comments that we did, the network parameters that it was working with, the operating modes, of course, the list of devices that I'm working with and that have been selected by the tool, type of cables, motors, and of course some messages that were had. At the end, always a disclaimer that you have to check everything that you do and how we do the calculation. And you're able also to see the one-line diagram depending on what you want. Here we printed out the one with the short circuit information. As you can see here with SIMATI Design, you're able to work only in the power side. If you need to change your controls voltage, as in 110, 220, or something like this, different tools may be used afterwards. But actually for you as panel builder OEM, this is a really nice tool actually to understand what's the effect of the short circuit, how it can actually help you in your design when you actually know the right short circuit current calculation and fault that might be available at the point of connection. Good. Now let me just save this test and I will go back to the conclusions. Well, now that I've shown you this example, let me just conclude with something really important for us. What we want to achieve actually is that with this type of tools, we want you to reduce the time and cost of creating actually a control panel. We want you to use less material. We want you to do a faster, easier design and engineering also on documentation. And of course, with a faster and wiring, saving you time and costs. Increase your profits. Give your customer actually what he needs. Customers often may think, well, I need a 50 kiloamp control panel. Remember, talk to them. Usually a lower breaking capacity is actually needed. And this you can actually achieve using the SIMATI Design tool and understanding why the short circuit changes this. Also, depending the markets, you will find easier to use fuses or unfused designs. This is also something that you have to speak with your customer about. Depending whether or not you need selectivity or backup protection, this will also influence a lot your costs, but this all comes in the design and in the engineering, and it will all depend basically in the short circuit calculation. This type of decisions you will make them here. Please remember this and always use, when you can, the SIMATI Design tools. Well, this was all for me today. I hope that actually you have enjoyed the webinar. It was a small introduction on the short circuit, as you can see, and telling you how it changes a lot. Maybe you have, and I have opened a lot of questions in your mind. Please, our experts are here in the chat and they can answer any question that you will have. We'll be here for a couple more minutes, so please send your questions. It was a pleasure for me to have you today, and I hope that you have enjoyed our webinar. We invite you for the next one. Always remember that we'll have more resources in siemens.com/controlpanel. Have a really nice day and goodbye.